Hey guys, I apologize for having a blank screen here for you at the moment, but I cannot get my little camera to work today. So next lecture, I should have that up and running for you. But in the meantime, I'm just going to go ahead and share my screen for our second chapter here, or second lecture, I should say, in our module. Okay. This moved. So chapter 2 is on atoms and bonds. Basically, guys, this is really basic chemistry. Basic being as simplified as you can get pretty much when it comes to what you need to know for this course for biology. So this is just going to go over, again, the basics. It's not going to go over all of the different rules for chemistry or how the elements on the periodic table are set up, what relationship they have. This is just going to go over what you need to know to get you through the rest of this semester, because this is a biology course, but we are all chemical at our lower levels of function. When I say lower levels, I really mean more at our primary levels of function. It's chemical interactions that make our bodies work. And so while we study larger systems for the most part in biology and larger topics, chemistry is essential to a basic understanding. Having said that, let's go ahead and look at our pre-lecture assignment. Again, please read these 2 pages, fill in the blanks before you watch this. Okay, matter. Matter is anything that takes up space and has mass. An element is one of the basic building blocks of matter. These are some of the elements on the periodic table. This is not the whole periodic table. Over 90% of the human body is composed of the same 4 elements, which you will see over and over throughout the semester: carbon, hydrogen, nitrogen, and oxygen. Okay. Chemists are going to arrange these elements again into the periodic table. And once more, the periodic table does show relationships on a variety of levels between the different elements. But we're not going to go into it for the class. All right, when we're talking about elements, we are going to talk about atoms. An atom is the smallest unit of an element that still has all of the properties, all the characteristics of that element. And it's made up of 3 particles. So first we have protons, which are found in the nucleus. They have a positive charge. Electrons are found in shells around the nucleus. When I say shells, I'm not talking about, seashells. It's more like if you think about a nut that has a shell around it, that kind of shell. And the neutrons are also in the nucleus. And they have no charge, they're neutral. And sorry, electrons have a negative charge. Okay, so these green guys are protons, brown guys are neutrons in the nucleus. Little yellow guys are orbiting, if you will. They're in these shells. And those are the electrons. Okay, so we need to know what the information on these individual blocks, if you will, on the periodic table, what this information is showing. I am going to cross out atomic mass because this is incorrect. I'll talk to you about that in a second. But we'll start up here with the atomic number. The atomic number shows the number of protons in the nucleus. The atomic number is super important because if you know the atomic number, you know what element you're dealing with. So in other words, this element here is carbon. Carbon has an atomic number of 6, meaning it has 6 protons in the nucleus. All types of carbon, carbon 12, carbon 13, they all have 6 protons in the nucleus, okay? Always. That does not change. So if you know the atomic number, you know the element, okay? Then you have the atomic symbol, which is right here. The atomic symbol obviously is the abbreviation that's used. C is for carbon. The atomic number is also important because in a neutral atom, one that doesn't have any charge on it, the atomic number, the number of protons, also tells you the number of electrons. And in a standard atom, also the number of neutrons. So I'm going to put neutral slash standard. In other words, it follows all the rules because of course this is science, so there are exceptions. But if the atom is a standard atom and it's a neutral atom, then the atomic number also tells you the number of protons and the number of electrons and neutrons. All right, the reason that this is wrong, mass number and atomic mass do not mean the same thing. They're not interchangeable. And this is in the process of being corrected, but it is not corrected on this sheet, so please cross it out. What you want to have here is mass, actually, I am not going to, we're not going to cross it off there because that is correct there. It's just wrong over here. So this is what you want to cross out, the one in parentheses, because again, they are not, you can't exchange these terms. The atomic mass is the average of all of the different carbon atoms that would exist. So they take a very large sample and basically weigh them, if you will, to get an average mass. And this includes isotopes. So on average, the mass of a carbon atom is 12.01. The mass number, however, this represents the sum of the protons and neutrons in the nucleus. The mass number is important when you start talking about isotopes. Okay, so again, sorry for the confusion. Cross out atomic mass where I have it crossed out in that little bullet point is not the same thing as mass number. The atomic mass is the average mass of all the carbon atoms, whereas the mass number, total number of protons and neutrons in the nucleus. Okay. All right. Let's move on. So electrons are going to follow certain rules. This is true. They are particles, subatomic particles of habit, if you will. Electrons, first off, they like to be in pairs. They really don't like to hang out alone. And this is really important when it comes to chemical bonding. What electrons like and don't like often determines what kinds of other atoms, other elements, I should say, they are willing to join with. Okay, so they like to be in pairs. Second, the electrons are going to be found in shells outside the nucleus. okay? They like to have their outer shells filled to capacity. Okay. So when it comes to shells, the inner shell can hold 2 electrons. And the outermost shell, which is called the valence shell, and this is what I will refer to it as we talk, valence shell, can hold 8. If you're studying chemistry more in depth, you'll find that there's more to it than this. And as far as we represent this as being very two-dimensional, but in reality, atoms are on, 3-dimensional levels. And so you'll get more information about how those shells are actually constructed. But for what we're doing in biology, this is really all you need to know. So again, valence shell is this outermost shell, and the electrons in it are often referred to as valence electrons. You'll notice that hydrogen is weird, and you're going to find that hydrogen is weird throughout this course, as it is in life. It has only the inner shell, so its inner shell is also its valence shell, and it only has 1 electron. And hydrogen also does not have any neutrons. That's right, hydrogens are nothing more than a proton and an electron. The configuration of the electrons in the valence shells are very important when it comes to chemical bonding, and again, deciding how atoms pair up with each other. Okay, so that's why you need to know the rules that electrons follow, because you will be asked in quizzes, and I believe on the midterm or one of your exams, to identify what type of bond an atom will be more likely to make. Okay, remember I told you that there are exceptions to the standard neutral atom. One of those exceptions is called an ion. Quite simply, an ion it's an atom that has a positive or a negative charge. Okay, so remember that in a neutral atom, you have the same number of protons as electrons. That means that those charges cancel each other out, and the atom is completely neutral. It's free of any charge. In an ion, however, there is a charge, meaning it does not have the same number of protons and electrons. So if it's an ion with a positive or negative charge, it's either lost or gained electrons. I know that it's common to think about atoms having a charge because it's either gained or lost a proton. So if I look at sodium, it has 11, atomic number of 11. Yep, it does. So sodium has an atomic number of 11, right? We would think that when sodium becomes an ion, becomes a positive ion, like, oh, so it must gain another proton to make it positive, right? Well, if sodium has an atomic number of 11 and it gains a proton, well, all of a sudden, that's not sodium anymore, because remember, the number of protons in an atom of an element always stays the same. So that means that all sodium atoms have to have 11 protons. If we had 12, it's not sodium anymore, it's magnesium. Okay, if it had 10, now it's neon. So we know we can't be moving protons around when it comes to ions. That means all we can move around are, again, the electrons. So in the case of sodium, if it's going to become a positive ion, it's going to have 11 protons, 11 neutrons, but how many electrons is it going to have? Try to answer that for a second. It's positive, so how many electrons is it going to have to make it positive? Hint, it doesn't have 11. It has 10. Okay, so the fact that it has 10 means it has one less electron than proton, giving this a positive charge. Okay, let's look at chlorine. Chlorine has an atomic number of 17. Okay, chlorine becomes a negative ion. So in this negative ion, you know, it's got to have 17 protons, because if it had one less, it would be sulfur. So it's not about moving protons, it has 17 protons, 17 neutrons. How many electrons is this going to have to make this a negative charge? It's going to have 18. Okay, it has one extra electron, one more than it does protons, making this negative. Okay. All right, this is important too, because ions like to get together, as shown here. Opposites attract. Positive charge likes the negative charge. When they get together, the whole molecule evens out, becomes neutral. Anybody know what happens when you add sodium and chlorine, or sodium and chloride? Know what you get? Table salt. NaCl, which, as you notice, is a completely neutral molecule because the charges cancel out. And this is salt. Okay. All right, let's keep going. By the way, I know this is a lot of information, especially if it's been a while since you've had chemistry, or if you just don't love it. I know it's a lot of information. Please reach out to me on anything you're not comfortable with, on anything you need more explanation for, and I will set up a time in this week for us to talk so that we can go over it and make it more comfortable. Okay. All right, let's look at molecules. Groups of atoms held together by chemical bonds are molecules. Okay. There are 3 types of bonds. I'm only going to cover 2 of them in this particular lecture. Oh, I gotta go back to my. I got all kinds of things going on. Hang on, too much stuff. There we go. Let's try it again. All right. Anyway, held together by chemical bonds, 3 types of bonds. Only talk about 2 of them in this lecture. Ionic, which, big surprise, between ions. Covalent, and hydrogen. We won't talk about hydrogen bonds till we get to the water lecture. And an ionic bond, again, formed between ions of opposite charges. Okay. So again, positively charged atoms attracted to negatively charged atoms. And I've already done the example up here for us, which is sodium chloride or salt. Okay, moving ahead. There we go. All right, let's talk about covalent bonds. Covalent bonds are shared between atoms. Ionic bonds you can kind of think about as being a transfer of electrons, where the one that becomes a positive ion essentially gives away one of its electrons to the one that becomes more negative. And so you can think of that as a transfer, but when it comes to a covalent bond, you can think of it as sharing molecules, or sharing electrons, forgive me. Okay, so when two or more atoms share one or more electrons. How do we know how many electrons can be shared? Well, that has to do with the valence electrons. So let's take a look at these valence electrons. We know that because of our electron rules, atoms like to have their valence shells completely filled with electrons, okay? Hydrogen can have two, right? It already has one, but it can have two. So how many more atoms could this bond with? Or how many more covalent bonds could it form? Shell holds two, has one. 2 minus 1 is 1. Okay. Hydrogen can form one bond, one covalent bond with one other atom. Okay. Let's look at oxygen. Oxygen has an atomic number of 8. The inner ring is full with 2, but the outer ring only has 6. Okay. So we know that it holds 8. It has 6. 8 minus 6 is 2. Oxygen can make 2 more covalent bonds, which works out super well when you're forming water, because oxygen has room for 2, and oxygen has 2 hydrogens attached to it when it forms H2O. Nitrogen has an atomic number of 7. Its outer shell has 2, 3, 4, 5. So again, this is going to hold 8. Has 5. 8 take away 5 is 3. It can form 3 covalent bonds. Then we get carbon. Carbon kind of likes to bond with like everything. Okay. That's why it's so essential for life. So it, again, this outer shell holds 8. It has 4. 8 take away 4 is 4. Carbon is looking for 4 other electrons to fill this outer shell. So it loves to bond, so it can get those 4 extra electrons. Okay, depending on how many electrons there are available, covalent bonds can either be single, meaning you're sharing one pair of electrons, double, meaning you're sharing 2 pairs, or triple, sharing 3 pairs. Okay. So if we're looking at hydrogen and oxygen, again, we're getting water, right? So hydrogen wants 1, oxygen wants another 1. Actually, hang on a second. That's confusing. Okay. And so when oxygen shares this electron with hydrogen, hydrogen essentially gets its second and oxygen gets its 5th. And then we're going to share this one, which is going to give oxygen its 8 on the outside. And hydrogen will have its second. I apologize because I'm not counting the electrons well. When hydrogen bonds with oxygen, it's its 6th electron. You kind of think of it as being right here. And then when it shares this electron, we get its 8th, which you can kind of think of as being the X, how they're sharing. That's what makes up water. While it's true that there are 2 electrons in the sense that you have 2 hydrogens, these are still considered single bonds because each hydrogen is only sharing 1 electron with the oxygen. All right, so if we look at oxygen gas, O2, we have 2 oxygen atoms, and they're going to share 2 electrons between them. Okay, so that makes this a double bond. Here we had 3 atoms in total. Here we only have 2. So it's a double bond because there's 2 pairs of electrons being shared between these atoms. Okay. Working in groups of 2, draw the following. I will draw one for you. It is super handy if you can attempt to draw the others, because this is a skill you will need to some extent for your quizzes. If you struggle with this, don't worry. That's normal. So if you're struggling, you're definitely not the only one, and you're definitely not the only one that's going to be reaching out to ask you to go over this with them. So please reach out. Okay, so I will start with CO2, which as we know is carbon dioxide. So if I'm looking at carbon dioxide, the first thing I have to know, I'm actually going to make a list of what you need to know. You need to know the atomic number. And we need to remember our electron rules for all of these. Okay, so for carbon, our atomic number is 6. And oxygen, our atomic number is 8. Okay, this helps us because we've got our nucleus. I'll start with oxygen. In fact, right, this is our oxygen. We know that it's going to have 1 ring, 1 shell that has 2 electrons in it, right? Because that's as full as that one can get. Now we're going to have a second shell. Oxygen's atomic number is 8. We have 2, so we know that we're going to have 6 in this outer shell, because 6 plus 2 is 8. Okay. Now let's do our carbon. we know that carbon is going to have 2. 8 take away 2 is, I'm sorry, carbon has 6, so it's going to have 2 here. 6 take away 2 is 4. Remember that this makes carbon really like to bond. And this is CO2, so we have another oxygen. So I'm just going to fill in real quick. Okay. Actually, for the sake of making this easier to see, I'm going to do it like this. Same number, I just put them in different locations. All right. How many bonds is this going to take? Okay. Well, let's take a look here. Oxygen has 2 electrons available that it can share. Carbon has 4. Well, that's great for carbon, but oxygen, at least this molecule, this atom, forgive me, only has 2 it can share. So it'll share this one here and this one here, and oxygen's maxed out. This atom of oxygen has nothing more to give. Carbon, however, is unsatisfied. It still has 2 more electrons. Well, that's where the second oxygen comes in. It's going to bond here and here. Okay. What that leaves us with, if I kind of demonstrate how it looks overall, forgive me for my silence. This is a little bit the tedious part here. Ah, it doesn't look like a circle, but it's okay. We're going to pretend like it is. Isn't that lovely? Okay. So essentially this shows how those electrons end up being shared. Since we have 2 electrons being shared between our oxygen and carbon, this means that we're dealing with a double covalent bond. Okay, so if I'm just going to get you started on H2, remember that we need to know the atomic number. Hydrogen has an atomic number of 1, and there's 2 of them, right? So you would have 2 hydrogen atoms. Hydrogen 1 and hydrogen 1. Oh, look at that. Okay. They share 1 between the 2 of them. So this is, okay. All right. Again, I'm not going to go through all of this in the lecture because it takes forever to draw, but I really, really encourage you to do it. And again, if you are struggling with this, please reach out to me and I will meet with you and we'll go over it. This is one of those things that repetition makes all the difference in the world, because it might seem overwhelming at first. And our brain kind of shuts down when it gets information that it considers as too overwhelming and too foreign. The way you work through that is repeated exposure. So in other words, working through issues like that, working through how many electrons, making yourself do problems that require you to think about how many electrons there are in ions, how many protons there are in specific elements. As you get used to that, it really becomes second nature, believe it or not, I promise. And you're hardly thinking about it. So please don't be overwhelmed. And if you are overwhelmed, reach out to me. All right, bond strength. Based off of the information that I have given you here between covalent ionic and hydrogen, the strongest is going to be our covalent bond. Everybody's happy because everybody's sharing. Ionic bonds are of intermediate strength. There's a lot of stuff that can break apart an ionic bond. And then hydrogen bonds are actually the weakest. And when I say that they're weak, they're still strong enough to hold water together, hold water molecules together. But compared to a covalent bond, they're the weakest. Okay. All right. So the last page. Let's talk about isotopes. This goes back to that whole, again, standard neutral atom, right? Well, we've already met one exception, which is the ion, the positively or negatively charged atom. And now we get to meet the isotope. And isn't it convenient that they both start with I? I swear whoever thought of that was like, I know, how can I take chemistry and make it more confusing? Let's start both of these exceptions to the rule with I's. Okay, so ion, positive or negatively charged atom. An isotope has the same atomic number, but different mass number, making you use your vocabulary. In other words, it has the same number of protons, but a different number of neutrons. Because if you recall, mass number is the total number of protons plus neutrons in the nucleus. Okay. So shown here are isotopes of carbon. Carbon-12 is your standard atom. It has 6 protons and 6 neutrons with a mass number of 12, 6 electrons, no charge. Carbon-13 is an isotope. Carbon-13 has 6 protons, 6 electrons, but look, this is called carbon-13 because the mass number is different, meaning that we have 7 neutrons because 6 plus 7 is 13. Carbon-14, well, we know it's going to have 6 protons and 6 electrons. So how many neutrons is it going to have to give us a mass number 14? That's right, 8. Isotopes have a variety of uses, everything from trying to get an age range for organic material to fighting cancer. Okay, some isotopes are radioactive. They give off high levels of energy as the isotope decays because isotopes are not stable. Carbon is supposed to have 12 neutrons, not 7, not 8. So when you have an isotope, those atoms are trying to get back to a more stable state, which means they're giving off energy. The energy comes as radiation. Okay. So again, what makes an isotope radioactive is when they spontaneously break apart or degrade and are unstable. And a lot of people think about things like plutonium and uranium and think about radioactive isotopes, because those are definitely very radioactive. However, we've used carbon for our example, so I will continue with that. Carbon 14, which again is up here, has 8 neutrons instead of only 6. Carbon 14 has something called a half-life. Actually, all isotopes have a half-life. The half-life means basically it tells you how long it takes for half of the sample to spontaneously break apart. So for carbon 14, it takes 6,000 years. 6,000 years for half the sample to break apart. So if I, as an example, I'm going to use a tiny number, but if you had 12 carbon 14 atoms in a sample that you found of something that had died, if you had 12 carbon 14 atoms in 6,000 years, you'd have 6. And in another 6,000 years, you'd have 3. Okay. And in another 6,000 years, you'd have 1.5. So this is how archaeologists, archaeobiologists, anthropologists, paleontologists, this is how they date organic matter that they find at their dig sites, is to measure the amount of carbon 14 that is left in the sample. Okay, so this type of dating method is called radiometric or carbon dating. Okay, question of the day, how do you find a tumor? Well, we use radioactive molecules. Okay, it's actually a bunch of radioactive molecules or isotopes that are used in medicine, both to identify and to treat a variety of different issues. There's something called a PET scan. It stands for positron emission tomography. Okay, it uses lower radiation molecules like carbon 13, which, if you remember, if you come up here, has 7 neutrons instead of only 6. Okay, this is lower radiation, meaning you're not getting nearly the dose of radioactive energy that you would get if you were exposed to the same amount of plutonium. Okay, so low radiation. And they can inject these molecules through a dye that gets absorbed by the different tumor tissues, tumor cells in the body. And when you do the PET scan, they glow. Okay. Radiation therapy, I'm going to skip down here since we're talking about identifying cancer. Radiation therapy, you get higher levels of radiation because higher levels of radiation are lethal to cells. So what's used as one type of radiation therapy is iodine 127. The fact that it's identified with a number shows that this is an isotope. This is also a larger or heavier isotope, meaning it gives off more radioactive energy. Yes, radiation is lethal to all cells, means the good ones and the cancer ones. That's why in radiation therapy, they try to target the specific location with a laser so that the radiation doesn't spread generally throughout the surrounding tissues. That generally still happens, however. Though you target the specific tumor or the location of the cancer, it is normal for radiation to travel beyond that point. Yes, that causes cell death in other parts of the surrounding tissues. And that includes even the white blood cells as part of the immune system. And general chemotherapy will also take out white blood cells. Okay, bouncing up here, Radioactive molecules are also used in sterilization. So again, carbon-13 can get used here. Sterilization of surgical equipment to make sure that there are no bacteria left or any other pathogen on the surface, so that surgical equipment can then be used on another patient. And the carbon-13 has, of course, worn off by the time it gets used on another patient. It's just there, it exists for the sterilization purposes. And it can also be used in produce. Yep. Okay. As always, as I've said throughout this whole thing, if you have questions, you are one of many that has questions. Please reach out to me. Please email me. Let's meet either in person or online so that I can go over this with you and it becomes more comfortable and familiar. Okay. All right. Good job. I will talk to you guys soon.